Good morning to all the attendees, everyone. My name is Chris Modrich. I am the manager of the sales team here at Lesman, and I will act as your host and moderator today. Today's webinar, titled How Do I Know If My Boiler is Out of Code, will be presented by Jim Kolbus of Clark-Reliance. Should you have any questions along the way during the presentation, please type them into the questions box, and I will make sure and get them covered either during or at the end of the presentation. Today, Jim will be going over the ASME boiler and vessel code details. He will show illustrations of common code violations and how to fix them, and explain the limitations for various types of direct and remote level indicator technologies. In this session, he will highlight water gauge glasses and remote level indicators, ASME Section 1 requirements for water level instruments for steam power boilers operating in excess of 15 psi. He will also talk about isolation and drain valve concerns and recommendations. He'll talk about the CSD1 requirements for low water cutoff devices, recommended blowdown procedure for level instruments, and of course, answer any questions you have along the way. A little bit about our speaker today. Jim has been with Clark-Reliance for 38 years and is currently a senior product manager for the boiler trim product line, where he specializes in level instrumentation. As a 30-year member of ASME, he has served on the research and development group for the Section 1 committee and is currently a member of the CSD1 committee. As a member of the American Boiler Manufacturers Association, he served on their board of directors from 2011 to 2015, and also as chairman of their I&C members and association groups. Jim earned his bachelor's degree in industrial management and mechanical engineering from David Myers College in Ohio. And today we welcome Jim back as a featured speaker and thank him for joining us and sharing his experience with our customers. And with all that, Jim, have at it.
All right, well, thank you, Chris. And welcome, everyone. We appreciate your time and attention to join us this morning, and we trust you'll find this presentation informative. We encourage you to ask questions. If we run out of time at the end of the presentation to answer all the questions, we will respond as a follow-up to all attendees with answers to those questions. So without further delay, we're going to proceed with our presentation. We are focused today on the areas at the boiler drum, as well as the areas in the control room where you see this operator looking at all the things that he monitors to operate that boiler safely. Also, from Clark-Reliance, we are represented in your area by Lesman. They're our partner for your area. And we do offer this boiler inspection guidelines booklet. I'll talk about it again at the end. But this is a 22-page document, and it covers everything we talk about today, as well as some additional details you may find helpful. These other names down at the bottom of this screen, those are the other product lines offered by Clark-Reliance and Lesman. So Chris pretty much went over our topic list today of what we're going to discuss. We'll be focusing on water gauge glasses, which are direct reading level indicating devices, the various technologies for remote level indicators. We are focused on Section 1 applications. However, there are critical non-Section 1, which are really Section 8 vessels that are vital to the success of the boiler, being feed water heaters, condensate tanks, and such. We'll touch on those with a slide or two. Preventing code violations, the specific requirements for isolation and drain valves, CSD requirements as they apply to low water cutouts. Also, a recommended blowdown procedure, which we contributed to the ASME boiler code, and there's even a reference to Clark-Reliance contributing this blowdown procedure that is in Section 7 of the code. Section 7 is titled Recommendations for the Proper Care of Power Boilers. It's about a 250-page document, and you can reach that through ASME. There's a lot of good helpful information in there for operators and owners. So as we begin, there are 4 types of direct reading gauge glasses. From left to right, there's tubular, and the tubular glass, they're typically 3/4 inch or 5/8 inch in outside diameter. The one that you're looking there on that water column happens to be tilted, And the reason the fluid up to the level line looks red, that's a red line tubular glass. There's a red stripe on the rear side running the entire length of the glass, and it's amplified up to the water line. So it does make the liquid appear as though it's red, but it's just telling you where the water line is with that red stripe. Many tubular glass installations are also clear without a red stripe. Tubular glass, I would say, is the least safe type of glass. It's the thinnest glass. It is rated by the glass manufacturers to 250 pound service. It's used on a lot of low pressure boilers, but be mindful if you're running into erosion situations where the glass is deteriorating from inside out and becoming cloudy rapidly, say in a few months, you might want to consider upgrading to one of the other types of gauges that will provide you longer service life. The second type of glass is a prismatic, also known as a reflex glass. There's a prism molded on the inner side of the glass that makes direct contact with the steam and water. Up to the water line, fills the prism with the liquid and prevents the prism from reflecting ambient light. So as a result, what you're actually doing is at the water line and below, looking into the back of the gauge, which is solid metal. There's only glass on the front side. So the water appears dark because you're looking into the back of the gauge. The area above that's reflecting ambient light appears white or grayish in color. These glasses are used in industry standards up to 350 pound service. The third type is a transparent flat glass, whereas there's flat glass on the front side and the back side of each window section of the gauge. What you're looking at here is an overlap of two sections, which is required by code and has been in the code since 1996. That transparent flat glass gauges must overlap by at least 1 inch so that the operator doesn't lose sight of the level. With a transparent gauge, these applications display water as clear, steam as clear. So if you lose sight of the line, you don't know if the level would be in the blind spot or full or empty. What you're looking at here is the gauge being backlit with a modern LED light, and it presents a star-like image in the window sections where the meniscus line is. How that works well is the lights are actually aimed uphill from the back side, so it illuminates that meniscus to look like a lighted bubble. The last type of gauge is a ported bicolor gauge. They can be used at any pressure up to 3,000 pound service. They're actually ports of glass and illuminated in such a way that water presents itself as green, steam presents itself as red, and due to the distinct color difference, ported gauges can be designed with no overlap. As you can see, we know right now in this 6-port example, the level is somewhere between the 3rd and 4th ports. Some of the additional code rules, and when I make reference to any of these PG sections, that is a subsection from within section 1 of the ASME boiler code. They do clarify that reflex gauges, when they are constructed in multiple sections, and this becomes necessary when the total range of the gauge needed for the application requires more than one section. Typically, one section of glass, maximum size 9 as an industry standard, provides about 12.5 inches of vision. When you need a vision range greater, that will turn into multiple section gauges. So this is an example. You can see there's a little void there between the lower and upper section. And if that water level line were right in that void, we would clearly see the bottom one black, the upper one white, and we would know that the level's in that blind spot. Off to the right, you see these figures showing the inner side of the glass that is in contact with steam and water. It is critically important whenever working on one of these gauges or rebuilding it that the prism's side of the glass be installed towards the steam and water. The outer side of the glass should feel smooth. if someone were to make a mistake and install the glass backwards, the glass tends to look full to the observer. So very important to follow instructions when working on gauge glasses. And this day and age, most everyone's got access to the internet, and all the major manufacturers have very good details of maintenance instructions. We have a complete library on our website, and we encourage questions, but never guess on working on these instruments. Always make sure you've got appropriate instructions, torque values, and procedures for this critical equipment. When it comes to a flat glass type gauge, Clark-Reliance is a bit unique. The first image in the lower left shows you a cross section of a Reliance gauge where we have individual finger clamps over the glass, which optimizes the load on the glass and gasketing. And these gauges perform very well. We have 4 different pressure classes, up to 2,000 pound service for these gauges. But what you're looking at there in the middle is a 3-section gauge designed with a minimum amount of overlap so that as the level climbs from bottom to top, it'll transfer over to the middle gauge, back over to the uppermost gauge without loss of indication of level throughout the entire range for the operator. Having said that, I'd like to bring to your attention the image shown on the right. Where that red arrow is, that's pointing to a structural web. Structural webs are used by process level gauge manufacturers, including ourselves. We have a Jurgensen brand of process level gauges that are used in countless applications for fluids other than steam and water. And that structural web, even though it has a hole through the center of it to pass the fluid, it can obstruct the operator's view of the level. Now, if you're looking at a fluid with color, such as oil or ethylene glycol, something like that, those webs might not be so disruptive. But if you put a gauge with those structural webs in the vision range of the glass, it can fool the operator to look like a water level line. In section 1 within PG 60, the wording is very clear to prohibit structural webs in the visual range of a gauge glass section. Now, where we do see this is in some of the large plants that have many process applications and only a few boilers. Sometimes the inappropriate technology migrates its way onto a boiler. So it's very important that you're aware of this. And boiler inspectors, who we work with very closely, and the insurance company inspectors are aware of this keenly in the training that they do, and they will look for this and recommend that it be immediately remedied if they see it. I mentioned earlier that the red and green is the way that the ported gauges depict the level. How all ported gauges operate is the glasses are not perfectly opposing each other. They're actually on a bit of an angle. It's a 10-degree offset in both directions. And these images that we're looking at on the left side, that's a plan view looking top down on the glass. So strategically located LEDs in red and green colors are feeding color into the rear side of the gauge, and the operator views the front side. When there is no water in the gauge, the red light comes straight through. As the water level rises, the red light is refracted out of position and the green light is refracted into place, and you distinctly see green water and red steam. A couple comments about ported gauges. They must be fitted with an illuminator in order to be code compliant. You could appreciate if we had no attachments on this gauge, we would have ports of glass with no colors and very difficult, less than a 40% chance to capture a meniscus line throughout the range of the gauge. The other thing I'd like to note is if you're using a ported gauge and you begin to see a red crescent moon in what should be all green as the gauge has changed, so to speak, that's a sign of deterioration on the mica shields on the inner side of the glass or dirt within the gauge, contamination. The first plan of attack should be to blow down that gauge glass and see if the sharp greens return fully. If not, it might just be time to rebuild that gauge. And one way to test that is to isolate the gauge, repair one port, both sides, return the gauge to service. You'll see a nice vivid green again, as well as the evidence on the parts you remove that would indicate to you that it's time to rebuild the rest of the gauge. Section 1 requirements, and I'd like to point out minimum requirements because a bit later I'm going to show you illustrations of how some plants install more than the minimum on the boiler in order to guard themselves against a single instrument breakdown for maintenance and still be able to be in compliance to operate that boiler safely. Any boiler rated to operate up to 400 pounds service is required to have at least one gauge glass in service at all times. No option to valve it off. Doesn't matter if you got 20 transmitters on that boiler, you're not shutting the gauge glass off. The bottom line to this point is there are too many low pressure boilers around a lot of people, be it a factory, a university powerhouse, a place where we could have students or workers on the other side of the wall from the boiler. It's just not going to be allowed. So this way, any low pressure boiler with a gauge glass on it in constant use, anytime the operator looks at that boiler, they'll be able to see the water level. Now, when you cross over 400 pounds, we start to get into the larger industrial applications, power plants, bigger facilities, and the code allows an option. The old way that was done 50 years ago was there was 2 direct reading gauge glasses in service in view of the operator, and an operator would be stationed out by the boiler 24/7. That's no longer the case. These days, we've got an operator sitting in a nice, comfortable, air-conditioned control room, like I showed you on that first slide. And what is required by code is they must have 2 independent, separate level indicating devices on continuous display. In addition to that, they must have a functional gauge glass. The gauge glass may be valved off, but it must be kept in good working order. So now, when you look at the logic, why are 2 level indicators required? These remote level indicators are instruments, not glass. So if we're trusting an instrument to tell us level, if we only had 1, how would we know it's correct? But if I'm an operator and I've got 2 separate instruments giving me very similar levels, they may deviate slightly, but similar, and they both track as level rises and falls in the drum. As an operator, I would have very high confidence in knowing where that level is. Now, suddenly, if one of those transmitters drifts, and now I've got a significant deviation between the 2 transmitters, how do I know which of the 2 is correct? This is where the gauge glass comes into play. I could use the gauge glass as my referee to determine which of the 2 transmitters is operating properly, and then take corrective actions on the one that is not reading properly. So keep in mind, this is code minimum, having additional gauge glasses, triple transmitters, quadruple transmitters I've seen in many plants. No one will ever complain about additional level instruments. So section 1 requirements, there are a couple specific rules that you should be aware of. And first, we're going to talk about fire tube boilers. And fire tube boilers have specific rules based on drum diameter. But we're going to look at 2 things. If you look at the range between bullets 4 and 6, that's the visible range of the glass. The glass is supposed to cover the full operating range. That would be from low water cutout at least up to high alarm. In addition, elevation at level 6 should never go any higher than level 1, which is the low side exterior of the steam pipe exiting the vessel. Level 4 cannot be any lower than elevation 2, which is the high side of the water pipe exiting the vessel. In addition to those 2 rules, there is a low vision requirement that's determined by the boiler manufacturer. They're going to determine the elevation inside the drum where if we get any lower, damage will occur. So when they determine that lowest danger point, you have to go above that to reach the bottom of the glass. So in this case, if I have a fire tube boiler with a 16-inch diameter vessel, that's a baby boiler, you might say, you've got to be 1 inch to the bottom of the glass, and typically the low water cutout is going to be about 1 inch above the bottom of the glass for confirmation. So this way, when you shut your boiler down, you've still got about a 2-inch safety bed of water in the boiler before any damage can occur. Simply put, you wouldn't want to trip your boiler with a low water cutout just as it's about to be suffering damage without some cushion or safety factor. When fire tube boilers exceed 16 inches in drum diameter, the minimum is 3 inches above the danger point to the bottom of the glass, and then the low water cutout still above the bottom of the glass. These rules are all found within section 1. When it comes to water tube boilers, the same rules apply as far as total vision range, staying out of the pipe diameters exiting the vessel. However, there's a tolerance now on the elevation above the danger point. No matter what drum diameter you have, the low vision must be set 2 to 3 inches above the danger point as determined by the boiler manufacturer, which is the one we're referring to here as level A. And once again, that gauge glass range must cover the full operating range, which would be a low water cutout up to high alarm. We'll look at an example now here. Here's a ported gauge, similar to what I'd mentioned earlier, with no lighting fixture on it. I took this photo myself. You can see there's no easy way to see the level, and someone might try to shine a flashlight on the back side, look in the front side, but keep in mind, if this gauge is operating at 1,500 pounds steam, that chamber is sitting there at about 600 degrees Fahrenheit or close to it. So I wouldn't want to get too close to it and slip and, bump your arm to it, whether you're wearing gloves or not. So when you look at the after photo, we retrofitted a new gauge. It's outfitted properly. Oh, I'm probably about 15 to 20 feet away from the gauge taking that photo, and you can see 4 green and 3 red, and we've got a bright overhead light here, kind of making those colors look a little lighter, but no doubt it's easy to read where that level is and very safe for an operator passing by. When it comes to remote or indirect level indicating technologies, first, there's conductivity probes. They've been used for many years. They were introduced to the market in about 1959. And these probes are sensors. As they make contact with water, a control unit responds by activating lights to indicate to the operator where the water level is. Second technology here is a magnetic level gauge, which is a stainless steel chamber containing a float. That float contains a magnet at the upper end of the float, and as the float rises and falls, corresponding to the level, this externally mounted indicator can be in a couple of styles. Some people call these flags, wafers, but they change like a Venetian blind on your window at home and flip up or down as the level changes. And each side of that flag has a different color on it. In this instance, one side's yellow, one side's black. ASME code requires that if you're using this type of device, you're not permitted to put switches on it. You are not permitted to exceed 900 pounds service. And there's some very specific reasons for that. I'll get into that just a bit later. Magnetic level gauges are commonly used and stem from the process industry. They started making their way onto boilers about 15 years ago, but there are some concerns for using them on boilers, and I'll talk about that later. Guided wave radar is a pulse technology with a sensing rod that reaches down into a chamber, and that is becoming more and more popular, and we see over time That'll replace what is the most commonly used remote level indicator and has been for many years, which is a differential pressure transmitter using a pressure static head at the upper piping and a lower reference leg out to a transmitter, and then sending that signal to a level indicator, typically in the control room. And these differential pressure transmitters are not maintenance free. I think people see that there's piping there all the time, but don't realize that some of that small diameter piping going to that level transmitter can suffer sediment buildup in that piping over time if it's not blown out periodically, even if it's done on an annual basis. We have proven errors over the years with DP transmitters when they were compared to conductivity probe devices. So earlier, when I mentioned that the code requires 2 transmitters on those high pressure boilers, or even if you can't see a gauge on a low pressure boiler where the operator's stationed, then they do need 2 transmitters. There's no rules about combining different technologies. So I could have 2 conductivity probes, I could have 1 conductivity and 1 differential pressure type. So the code just requires 2 separate devices, the same or different technology. I would recommend using 2 technologies because 2 technologies can't fail in the same manner. So that would improve or lower your risk. On magnetic level gauges, the indication scale must follow the same rules we just talked about with the gauge glass, not encroaching into those vessel connections. You cannot attach a gauge glass onto a magnetic level gauge. If someone were to do that, that's making a water column out of the gauge glass out of the magnetic level gauge. And those magnetic level gauges are constructed from stainless steel so that the magnet on the float doesn't just attract to the chamber and stick in one spot as it would do if the chamber were made from carbon steel. The code only permits 3 materials for water columns: ductile iron, cast iron, or carbon steel pipe. Stainless steel is not permitted for the construction of a water column. In the process world, magnetic level gauges often replace gauge glasses, especially in some of the very harsh service fluids. However, in this case, on a Section 1 boiler, a magnetic level gauge may not be used to replace the code required gauge glass. It can fool an operator because you're looking at a level mounted on this device right where a gauge glass was before, but you're still relying on the magnetic field to attract that indicator, and it's not the same as looking directly at a glass. Okay, here's an example of a magnetic level gauge that was installed with a scale that was too long and it was too low. And the problem with that is that lower end of that scale will never change because we'll have trapped level in that chamber. And with magnetic level gauges, you need a chamber that runs a significant distance vertically below the lower side connection in order to accommodate the length of the float. Typical floats for magnetic level gauges start at about 12 inches in length. And that's why there's a flange on the bottom so that someone can access the float for inspection. So what's happening here on this same application is the technician here has retrofitted a code correct indication scale corresponding to the range, operating range of the boiler. So we had a problem and it was remedied. Next, here's an example of that operator looking at 2 independent level indicators of the same technology that are being used to operate this boiler. So he can see 2 levels running at normal, and in this case, he's satisfied. What you don't want to do is have, say, a 4 to 20 milliamp signal feeding one of your required level indicators into one of these screens that he may have to change to look at other aspects of the plant. So if you are using a screen for level indicators, must be done like this image off to the right. This is in a different plant, and what we've got here are 2 units with 3 drums each. On the monitors below, we're looking at differential pressure transmitters, and on these indicators above, those are from conductivity probe devices. And you'll see each one of these are corresponding with the same levels. Now, this 4th drum over from the left is empty, showing dry, but that unit was out of service at the moment we took this photo. But again, if I were in that operator's chair, I got 2 different technologies for each drum, and they're all reading comparably. So here again, high confidence in how these level transmitters are operating. And these screens never change down below. Here's an example of a user. Now they're running a low pressure. These are reflex gauges with 2 sections because they exceeded what the maximum limit was of a single section glass. So what this plant is doing, they got a conductivity probe device in the center. And a conductivity probe device can be used to support gauge glasses because that chamber is carbon steel. So it can serve as a water column. But if we look at all the equipment on this drum, we've got 2 gauge glasses. Only one is required because this plant operates below 400-pound service, but they have a second on here as a spare in the event that one needs to be isolated for maintenance. They have the conductivity probe device and 2 differential pressure transmitters here, so they've got a total of 3 remote level indicators. If any one of those 3 is out of service for maintenance, they're still in compliance and can still operate that boiler within compliance of the code. Next, I'd like to talk about piping requirements. The minimum pipe size from the drum to a water column or a low water cutout device is 1 inch. The minimum drain size off of a water column or a low water cutout device is 3/4 inch piping. I'd also like to note gauge cocks. The boiler code refers to gauge cocks, or also known as tricocks, which are these 3 valves that are on the side of a water column. For many years, they were used as a standard in addition to a gauge glass. If we go back in time prior to 1991, the ASME boiler code required low pressure boilers to have either 2 gauge glasses or 1 glass and these 3 tricocks. When you open up the valves, they vent to atmosphere. There's a little nozzle on these, and my middle one is normal water level. So what would happen is open the top valve, you'll see a stream of steam, so to speak, or a plume of steam. When you get to the normal level or low level and you're in a water situation, it'll squirt out that nozzle, a stream of water, just like water out of a garden hose. Over time, this technology has faded in popularity. You know, these valves, when they fatigue, they can leak, they can drip hot water. Since 1991, the code looked at the reliability of low pressure glasses and simply eliminated tricocks as stating that they are not required, and you can get by with only 1 gauge glass if you wish. Having said that, we still have a lot of users in plants who continue to use those 3 tricocks. We still sell them, but they have not been required since 1991. Any boilers manufactured in the last couple decades, most manufacturers are not including that additional cost unless it's customer specified. They know the code, and you'd find yourself hard pressed to see the 3 tricocks on a water column on a new boiler installation. Isolation and drain valves are required for all externally mounted level indicating devices. Every gauge glass must have its own set of isolation and drain valves. Every remote level indicator, no matter what technology, must have its own set of isolation valves. Double isolation valves are permitted. There's nothing wrong with doing that. However, drain piping going out of those drain valves should be operated and routed to a safe location. A safe location is not a pipe stub aimed right at the operator's feet while they're standing there manipulating the valve. The other problem with short pipe stubs coming off those drains is as that cloud is forming, whether an operator is wearing a glove typically to reach your hand back into that cloud, finding the handle of that valve is not a pleasant thing to do. ASME code requires specifically on applications over 100 PSI that the drain valve be routed to a safe point of discharge. All low water cutouts in CSD1 are now requiring those drains to route to a safe discharge. Isolation and drain valves themselves. Gate valves have been permitted to be used ever since boilers been in existence. The problem with gate valves is they need to be run in either full open or full closed mode on these level instruments. These level instruments are used and blown down regularly by operators. So the rapid flow of steam and water rushing through these valves can wear away at the bottom of the gate if that valve is not full open, if it's partially left open. So as a result, often in high pressure steam service, gate valves don't provide the service life that one would expect out of a boiler valve. Ball valves are permitted. The only concern about ball valves is it's hard to do a slow open and slow close if you're trying to be careful about putting an instrument into service and watching for leaks. As a result, there became a higher demand to use globe valve in the boiler industry, I would say going back about 20 years. And I'm showing an incorrect globe valve here first. This is a typical globe valve where the stem is at a right angle to the flow. And by typical design of this standard globe valve, there's a natural trap in the valve that could very easily plug with sediment over time. And there's no way to rod this valve. So due to petitioning of ASME code, going back in about 2006, it became within the code in PG 60, the rules for the use of globe valves in the 2007 edition of the code that requires the use of a globe valve is permissible if the 1/4 of the inlet port diameter is above the seat when the valve is open. So this section view here shows a Y pattern valve, and this upward angle is where the operating stem would be. And you could look at this valve. If the valve were loose and you were holding it in your hand, you could see light straight through this valve when the valve is open, or insert a rod all the way through the valve when the valve is open. So this valve is very resistant to sedimentation buildup or particulate buildup within the valve. Operating chains on water gauge valves. This is also an important thing. The code requires an operating mechanism anytime a bottom or top valve is more than 7 feet above the operating floor or platform. When you think about the average height of a boiler operator, anyone reaching their hands over their head could get to 7 feet, but anything more than that, you need a step stool or a ladder, and that's what the code wants to prevent accidents. So they don't use the word chain in the code, but the chain is the most common word. The word you'll find in the code is an operating mechanism, which could be a chain, could be reach rods, could be automated valves, but typically chains are used. And in this illustration in the top center, we have quarter turn valves that in this position that they're shown now, this left handle is pulled down to open both valves. And if I pull this handle on the right to close both valves, they would both be shut tight. So when properly instructed on these valves, when I see the right hand at this lever at about a 2 o'clock position, the valve's open. When it's at about a 5 o'clock position, the valve would be closed. When you have chain wheel valves, they're typically installed on single pitch thread valves. So those wheels probably have to spin 2, 3.5 times perhaps for that valve to be either full closed or full open. These valves to be properly installed, must have independent chains for each wheel. Water gauge manufacturers extend the stem on the upper valve further so that these chains don't tangle each other, and each valve is operated independently. It's extraordinarily difficult to manufacture these valves in multiples where you could end up with the teeth on the chain wheel sprockets in exactly the same position when the valves are closed. So what would happen if I were to do a bicycle chain arrangement on both of these chain wheels, the first valve to close stops the chain, and then you have a situation where an operator says, hey, I can't get these valves to shut tight. We'll ask for a photo of the installation, see the bicycle chain and say, folks, change the chain, put a loop on each valve, and then they'll report back to us and say everything's working fine now. For an easy way to determine the position of these valves, we at Clark-Reliance started installing these tags on the chains right near the chain guide at the top of the valve here when the valve is closed. So the operator learns quickly where that tag is right underneath the chain guide. That's when the valve is closed. When the valve is open, that tag would be down at a lower elevation. So it's about instructions and training, and once you know a thing or two about these valves, you understand lever position or chain wheel position for safe operation. Here's an example. I'd like to point a couple things out. This is a 15-foot ladder. You can see these chains elevating or eliminating the need for the operator to ever use a ladder. The purpose of the ladder this moment in time was they just installed a new illuminator on this gauge. And if you look closely, you can see the elevation in that flat glass gauge with that LED light. But you do see the chains dropping down, so as a normal course of operation, the operator does not need a ladder. This case here off to the right is showing this operator taking a look in the gauge. The thing here, you can appreciate there's no way that he could reach this upper valve without a chain. The problem with this installation, however, is they've got that chain like a bicycle chain between those two chain wheels, and I can almost assure them they will not get tight shutoff on both valves. Can't tell you which one, but either the water or the steam valve will shut tight when that chain's pulled, but very likely not both. Okay, here's a serious installation on a new water column in gauge glass. If you notice here that the steam and water piping coming off of the boiler is sloping downhill to the water column. This was a very serious error. You see the middle of the gauge glass is at the same elevation as the water tap coming off the drum. So the lower portion of this glass, the conductivity probes that are in this water column for low alarm and low cutout are always going to be satisfied with water because of this misinstallation. I don't have an after photo, but this was remedied and these pipes were reinstalled horizontally rather than drooping downhill. So this is a very serious consequence. If they had operated the boiler in this installation, they could have put that boiler at risk. Couple of additional concerns here. This little boss that you see on the lower water gauge valve here is supposed to be welded to a drain valve routed to a safe location, but being that there's no drain valve here, there is no way to isolate this gauge glass and drain it without draining the boiler. This was remedied, but during installation, someone just welded that port shut and had an immediate violation. This is a magnetic level gauge shown off to the right. And I'd like to point out again, they've got this lower part of the scale below the water leg feeding that chamber. And if you look casually at magnetic level gauges on the websites for different manufacturers, you'll see a lot of manufacturers showing the scale of indication going into and above the upper connection and into and below the lower connection. But you also have to consider in a lot of process fluids, such as a static tank of fuel or oil just sitting there, there would be no harm or foul by having a false level indication at the extremes. But having said that, we know how serious those consequences could be on a boiler. So the rules are very specific on boilers that these scales for indication cannot go into these pipe diameters. How someone would remedy this would be maybe riveting on a plate to cover the parts of the scale that you shouldn't see, or order a new scale from the manufacturer, as I showed you earlier. Some examples of low water cutoff devices include conductivity probe devices or float switches. Probes can also be installed directly into a water column. Floats can be installed directly into a water column, but these are the most common technologies. It was mentioned earlier that I'm a member of CSD1. ASME CSD1 is a publication for controls and safety devices for automatically fired boilers. These rules apply to boilers that have a fuel input range up to 12,500,000 BTU per hour. The subsection of CSD1 that covers low water cutouts on steam boilers is CW140. They require two separate devices in separate chambers. They require that each device be fed from a separate water pipe coming off the drum. However, they can share the same steam pipe coming off the drum. The reason for this is if one water leg becomes contaminated with sediment buildup, it does not affect both devices. Just as I mentioned for water columns, the minimum connection size to the vessel or drum is 1 inch, and the minimum drain size is at least 3/4 inches. And one of the devices could go right inside the boiler. That's commonly done on many low pressure industrial boilers used, say, in dry cleaning or low industrial application needs. Here's an error with low water cutouts on a CSD1 application because CSD1 does not permit the use of isolation valves between low water cutouts and the boiler. The reason being, we could have an unauthorized person close a valve, trip a boiler, and maybe the operator in a remote location might not know what's happening. That's just one example why those valves are not permitted between low water cutouts and the boiler on a CSD1 jurisdiction application. I mentioned earlier, some of these other applications, you still should take the time to check these application instruments, make sure that they're operating properly, maintained properly. These include deaerators, condensate tanks, blowdown tanks, and feed water heaters. While these are not Section 1 because they're not fired vessels, they're Section 8 vessels. Some of the rules are a little different, but many times we'll find users adopting Section 1 rules for level instruments because there's no clear definition for instrument requirements within Section 8. So you see here on the left the tubular glass that's overlapping as an example of one of those Section 1 rules. But some of the products we've been talking about, reflex transparent gauges, magnetic level gauges, those are common economic solutions to level instruments used on these types of applications. To touch on some maintenance tips for you today, all these devices should be inspected regularly and valves routinely to look for wear or leakage. Any steam leak should be remedied as soon as it's discovered. If steam leaks are allowed to persist, what the result will be is damage in a cavity of a valve, which will require replacement, maybe damage to insulation, packing, valve stems. The cost of the repair escalates if the item is permitted to leak for an extended period of time. So plan your annual maintenance intervals, document your repairs to track your repairs and see what could be done to make improvements. Maintain all your insulation on all your piping leading up to instruments. for operation purposes as well as personnel safety. If your application is subject to freezing conditions, we'd recommend heat tracing on all the piping and the instruments so that you don't suffer any damage to those instruments in freezing situations. Use OEM parts for any instrument you have. The OEM knows best as far as any updates, changes to gasket materials, changes to specifications they may make, and most importantly, torque values. If I under tighten a level instrument such as a gauge glass, it'll leak ahead of its time. If I over torque the fasteners on a gauge glass, I could cause damage to the glass or short service life. So it's very important to follow procedures. When you conduct blowdowns, we recommend that they be done properly, not excessively. Clark-Reliance has a blowdown procedure that you can find on our website. The video on our website takes about 6 minutes to watch, but we recommend the procedure not taking more than about 20 seconds. You open a drain valve and watch for 20 seconds. It's plenty of time to see water drop out and a line clear, and if you're blowing steam out the drain. If we look at this illustration, this is just a snippet of what you'd see in that blowdown procedure on our website. I'd like to show you a typical installation here where valves between the water column and the drum are optional by code, but the valves between a gauge glass or a level indicator and the drum are required. But if an operator simply opens a drain valve, either on a water column or at the bottom of a level instrument, steam and water are both fighting to go out that drain. So in theory, I could have a totally blocked water leg here with sediment and debris, but steam would still blow out whatever water is in that glass out the drain, and I would never know that I have a problem here. If I isolate both steam valves, then open the drain, I'm flushing the water line by itself, blowing out any contaminants, and then closing the water valves, opening the steam, finishing with a steam blow in case I've released some debris into that gauge glass or in that piping. Then close that drain valve and open those water valves and return everything to service. I've given you a very quick explanation on a 6-minute video here. The same philosophy applies to conductivity probe devices. Whenever doing blowdowns, it's always important to bypass a low water trip so that you don't trip the boiler needlessly and that the operator knows that someone else will be conducting a blowdown. On conductivity probe devices, the piping can be very simple, but as I mentioned a moment ago, the procedure is the same. Isolate the steam, blow the water leg out first, then close the water, finish with steam, then close the drain valve and open the water, and the level returns. Our video is an animation that shows you movement of steam and water and a very nice detail on these procedures. We've got a lot of helpful information on our website, including policies, practices for these critical instruments on your boilers, order selection worksheets, maintenance instructions, things that are very helpful to you. So feel free to contact any of your friends at Lesman or one of our application engineers. If you need help from other resources or you want to check on information for your specific area, contact your local jurisdiction inspector, contact your insurance company. They are enforcers of the code rules. Plant reliability engineers can be beneficial if you need added support within your businesses. Excuse me. We at Clark-Reliance and Lesman can provide local training for you, visit you. We can do recommendations. We can do virtual surveys now with these COVID times. We've done a number of those successfully by having someone take either a series of photos or do a live virtual survey while someone's there at site and we're tuned in remotely and make recommendations. We're a widely recognized source for doing this training. We've been doing this training for boiler inspectors and insurance companies dating back to about 2001. So we've got a 20-year history of having a document to summarize the code rules that is in that book that I described earlier. And that all started with a presentation we did at the Chief Boilers Seminar many years ago at the National Board. So we continue to update that book every 2 years to be in step with the code. Clark-Reliance has a YouTube channel with a lot of helpful information on all of our products. Feel free to go there. And I just want to mention we have some videos on our specific products that you might turn to for a solution to some of your gauge glass problems. In this application, this operator doesn't have to climb that last flight of steps to see the level in his gauge that he used to. If you go to our animation and video at Simpliport180.com, it's about a 2.5-minute video showing this gentleman, who is not a Clark-Reliance employee, viewing the glass and telling you how easy it is, and it's the best glass he's ever seen. When you compare a Clark-Reliance Simpliport gauge to the other manufacturers in the industry, they tend to show the images like vertical rectangles or slots. And these are all ported gauges. Our gauge looks most port-like out of all gauges in the industry. For our conductivity probe device, for 7 years now, we've had a SmartLevel, as we call it. This instrument was improved where we have a microprocessor, independent one for each probe level, and we have a blue warning light that alerts the operator before you get a false signal that the sensors are beginning to get contaminated. It works much like a check engine light in your automobile, as well as all these LEDs now protrude out the front of the indicator to provide full 180-degree viewing from the surface of this panel. We've added white lights to highlight the normal water level for the operator and a green system status indicator, letting the operator know that all the systems are communicating. There's a few-minute animation of this product and how it operates at this website. Excuse me, folks. A lot of talking here in the last hour. So contact Lesman for a complimentary copy of this boiler inspection guidelines. You can also contact one of our Reliance application engineers. You're welcome to contact myself, Jim Kolbus. And I want to thank you all for your time. And I'm going to turn it back over to Chris now, if he's got any comments or questions, or we're about ready to wrap it up. Chris?
Jim, thanks. Excellent job as always. During the presentation, nobody asked any questions. So if you would like to now, here's your opportunity. Just you can type them right into the questions box. So meanwhile, thanks to everybody for attending. Should you need any additional information, contact your Lesman salesperson if you know them. If you don't, you can call 1-800-953-7626, or you can email me direct. I'm Chris M. at Lesman, CHRISM@Lesman.com, and we'll find someone to help you. Last call for questions if anybody cares to type. I don't see any. Jim, thanks again. You make it very compelling, and you're a great presenter, and we really appreciate your time. Everybody else, thanks. Wish you all a pleasant and safe and productive day, and thanks for joining our webinar today. And watch your email for more. We're always trying to teach people what they need to know. So thanks to everybody, and this is officially the end of this presentation.
Everyone have a great day. Thank you again.